G'day team, welcome back to another video on the applications of differential calculus. Now today we're going to look at the final thing in our little unit here, in our little playlist, and that is going to be optimization. Now we have, again, like I said in the previous video, done this before in our introduction to calculus, but we're going to look at some slightly trickier sort of examples. But optimal solutions, they occur at the maximum or minimums of my function f of x, or any other function, in this case for my example down here, c of x. We can use sign diagrams in our calculator to find locations of maximums and minimums. We could do a first derivative test where we find the sign diagram. This is an increasing, decreasing. There's our maximum, there's our minimum. So we know that from our stationary points. Or we could do a second derivative test. And if my second derivative is less than 0, I'm concave down, so I've got a maximum. And if my second derivative is greater than 0, I'm concave up, so I've got a minimum. So there's a range of different ways we can solve these problems. The trickiest is actually getting the equation from a diagram. Now, I'm not going to go through an example of a question where you have to pull the example or the equation from the diagram, but if there's a bit of a need for it, I can definitely do one later down the line. So we're going to have a look at this question here. Now, this is finding how many kettles should be manufactured to keep cost to a minimum. So that means X is the number of kettles. I need at least 10 kettles, all right? And this is my cost function here. Now, I personally think the easiest way to solve these is to do the first derivative test, all right, because that tells me exactly where my maximum and minimum values are for the variable I'm trying to find. So what that entails is finding my derivative. Now, looking at what I've got here in my function, I've got two functions of x added together, so I can look at them individually. Now, for ln x, we know nice and simply goes to 4 on x. So the derivative of ln x is 1 on x, and I times it by 4. Now the trickier one here is in fact this little guy in here, but it is just a little chain rule. So I've got the 2 that comes out the front, so plus 2. Rewrite the inside, 30 minus x all over 10. Drop the power by 1, and now we have to times by the derivative of the inside. Now this is a bit trickier to spot, but inside here, essentially we've got 30 over 10 minus 1 over 10x. Now the derivative of negative 1 over 10x is negative 1 over 10. So let's just tidy that up a little bit. 4 over x minus 1 over 5, but I can put that inside there and make that 50. So I've got 30 minus x all over 50. So that there is my derivative. Now this looks a bit gross, but what we can do is actually simplify this a little bit so we can solve this by hand. So we're going to do that together, and I want to set my derivative to equal 0. So I've got 0 equals 4 over x minus 30, take away x all over 50. Now the easiest way to sort of get all of this by itself, I can even get rid of these brackets now, is to cross multiply. So let's do that now, or even, yeah, let's cross multiply. So I've got 4 times 50, so that's going to give me 200, minus x times 30 minus x, all over 50x, and that's all equal to 0. And the beauty of what we've just done is we can now ignore the bottom here and solve just the top for x. So 0 equals 200, take 30x plus x squared, and I might just rewrite this in the way we like it. So x squared minus 30x plus 200 is equal to 0. Now, this looks like a complicated quadratic, but we can easily sums and products this. I've got two numbers that I need to multiply to 20, but add up to negative 30. That is both negative got -10 and -20. So therefore my two x solutions are 10 and 20. So these are the values I put on my sign diagram. So over here, I need, actually, because I've got a limit, I need at least x greater than or equal to 10. So 10 is my lower limit. I can't go lower than that. I've got 20. This is x, and this is for my function c prime of x, my first derivative. If I put something into my equation that's in between 10 and 20, say 11, I've got 11 minus 10, which is positive, 11 minus 20, which is negative. So I've got a negative, and then I've got a positive here. So we can see I've got a minimum at x equals 20. Therefore, to minimize cost, the company should make 20 kettles. And what we can actually do is find that minimum cost. So let me just jump up here and grab my cost equation. So that's here, duplicate, bring that down. So I'm going to substitute 20 into that cost function. 4 ln 20 plus 30 take 20 on 10 squared. Now 30 take 20 is 10. 10 over 10 is 1. 1 squared is 1. So all of that is just 1. So I've actually got 4 ln of 20 plus 1, which is $12.98. And that is the minimum cost to make 20 kettles. Hopefully this helps. We can obviously use our calculator to solve a lot of this nice and quickly, but it is really important to see just in case they do throw some extra unknowns in there. Thank you for watching, and I hope to see you in the next video.